Welcome back. You know from what we've done before that catalysts are usually transition metals and they usually need a high temperature to work. So we need a high temperature. We don't really want a high temperature, but actually the benefits of having the catalyst is better than not. So that's why they do it. So there is a compromise that has to be set up. So the compromise is 450 degrees for our catalyst to work, or the reaction is too slow. So we've got this, which is quite useful so far. Just to help you understand what the catalyst actually does, if you think about nitrogen, the nitrogen molecule N2, between the nitrogens there's actually there's a triple bond, and that actually is a really strong bond. That's why it's so stable, that's why it doesn't react and really pretty boring most of the time. So what they've got to do is they've got to try and break that up, and that's what the catalyst does, is it breaks that bond so the reaction can happen more quickly. Just a little minor point you might want to know. Okay, so we're almost there. This is the actual, if you like, a simple way of looking at the Haber process. So we've got our raw materials, our nitrogen and our hydrogen coming in here, putting under high pressure, to remember to hopefully increase the reaction, forwards reaction. It then goes into this chamber here, which is at a very high temperature, 450 degrees, and it's forced through the catalyst. And as it comes through the catalyst at high pressure and high temperature, it will change to ammonia. Over here we've got a cooling area, and that means it's going to take the ammonia out, as the ammonia boiling point is higher, so they can cool it down so it becomes a liquid. That can get tapped off. Remember, it's always a good thing if they can remove those, it means the pressure is going to get lower. And then they're going to put back into the system the raw materials that haven't, or the reactants that haven't actually been used up in the first reaction. What they found is actually doing it just once, you only got a yield of 5%. That's rubbish. And as a manufacturer, you think that was cack, really, the amount of money you spent to get to this point. So that's why it's re-pumped around the system again. Doing it this way, you can get a yield of around 95%, so it's actually worth it in the end. So it's quite a nice simple system, but we need to remember the keys are: it's quite hot, that's an expense. The catalyst itself will be refined, that's expensive. And the third thing, which is the most expensive thing, it's the walls here must be exceedingly thick to be able to withstand the high pressure that it's at. So it's actually a very expensive thing to produce ammonia gas. So this is our final thing, just to summarise. Here we've got our equation, our 4 molecules on this side, 2 on that side, our nitrogen and our hydrogen, reversible reaction, becoming ammonia. But we've managed to force the forward reaction by increasing the pressure, as there's less molecules on this side than there is here, and by using